In this module, we are going to learn about the different non-parametric tests related to especially the ANOVA that is where, as you know, that in ANOVA there are some parametric assumptions. When it doesn't hold, then you have no other choice than apply a non-parametric test. Mainly, we are focusing on in this module the first is the two-way ANOVA or repeated measure ANOVA. The alternative of two-way and repeated measure ANOVA is a Fragment test, and then the postdoc test corresponding to the Fragment test, and then how to get the empirical distribution function and the density, how to get a density function to get that idea about the distribution non-parametrically, and then finally we will know how to apply the Kolmograph's mean-of test, that when sometimes that cumulative distribution or empirical distribution function may not help you to get a complete idea about the distribution of the test while you are comparing or trying to match with some parametric distribution. In that case, statistical test like Kolmograph's mean-of test might help us to identify whether that particular data supporting this distribution or not, or sometimes the measure of goodness, the goodness of fit test can be done through the Kolmograph's mean-of test instead of chi-square test. So we learned the Kolmograph's mean-of test in R, how to use those in R. In this module, we will discuss few more non-parametric tests. It's a continuation of the previous module. We'll start with the Fragment rank sum test. The Fragment test can be used for analyzing the unreplicated complete block design. For example, there is exactly one observation in Y yield of each combination of levels of groups and blocks, where the normality assumptions may be violated. The null hypothesis is that apart from an effect of blocks, the locations parameter of Y is the same in each of the group. If Y is a matrix, the groups and the blocks are obtained from the columns and the row indices respectively. The NAs are not allowed in groups and blocks. If Y contains NAs corresponding to block are removed. The uses of this function called Fragment.test from stats package are three ways you can use, only the Fragment.test pass only Y, Fragment test Y stratified by groups and blocks, Fragment.test then in a formula format. Formula format is more convenient compared to others. The pass by arguments are the Y is either a numeric vector of data values or a data matrix. Groups a vector giving the group for the corresponding elements of Y. If this is a vector, ignored if Y is matrix. If not a factor objects, it is coursed to 1. Blocks a vector giving the block for corresponding elements of Y. If there is a vector, ignored if Y is matrix. If not a factor object, it is coursed with 1. A formula structure is as earlier, A tilde sign B given C. C is the block. The argument data, an optional matrix or data frame containing the variables in the formula. By default, the variables are taken from environment formula. The subset, an optional vector specifying the subset of the observation to be used. It is, if you do the test for a subset of the data, this variable can, this argument can be used to get the subset or the selected portion of the data. NA.action for the missing values. If the data contain missing values, NA.action will help you to exclude all the missing values from the data before apply the Fragment test. Next, we'll see the one example in a comparison of three methods: round out, narrow angle and wide angle for rounding first base. For each 18 players and the three methods, the average time of 2 runs from a point on first base line 35 feet from home plate to a point of 15 feet short of second base is recorded. Here is the data that has been entered in R from that data given in that book. That rounding time is in a matrix form. 3 columns that round. The first one is a round out, second one is a narrow angle, and the third column is the wide angle. The name also has been given there. So the total number of rows are 22. And then if you can see the data, the header of the rounding time data frame looks like this, and the tail looks like this. Total 22 data points are there, 22. The Fragment test can be applied. The Fragment.test rounding table, if you can pass this data frame, it will generate the results of the first way of generating Fragment test result out of the 3 that I have shown. So it will give you the Fragment chi-square test statistics, degrees of freedom, and p-value. Here p-value is 0.003. So strong evidence against the null that the methods are equivalent with respect to the speed. The second way that we can write WD equals to another example. So WB equals to aggregate. This is the warp P breaks data that we dollar breaks by list. That means this variable would be aggregated by two factors is the wool, another factor is tension. That function equals to mean. So this way the WB will the data would display like this. Then Fragment test can be applied patching these 3 column together, say WB dollar X, WB dollar W, and WB dollar T. The first variable, first argument should be the numeric value, and the second 2 arguments should be the 2 stratified variables, and that will generate the p-value. P-value generate the Fragment test results, statistics, degrees of freedom, and p-value. The p-value is 0.56, which is not at all significant. The third way of doing a Fragment test is a Fragment.test X tilde sign W given T data equals to WB, and that is the p-value is 0.056. The same test that we did in terms of this format. And the p-value as usual is not significant. It's the same results of the previous slides, but arguments are given in a different format. The Fragment postdoc test. Provided that the Fragment test indicates a significance, the postdoc test, according to the Nemeni 1963, can be employed. Such 1997, page number 668. This test requires a balanced design. So N1 equals to N2, Nk equals to N for each group, and each group K, and a Fragment type ranking of data. So say record package PMCMR and use this data Y equals to matrix. This enter the matrix, number of columns, 6 by 6 matrix, that 6 variables and 6 individuals data, say looks like this. The data, the box plots also, if you do the box plots also looks like this. So that means there are 6 parameters, A, B, C, D, E, F, and total number of rows are 6, 1, 2, 3, 4, 5, 6. And the box plot will give you some idea that probably they would be statistically significant. They are significantly different because not all the boxes are overlapping each other. Few are quite distinct. So Fragment test can be applied. So Fragment.test Y, that will give you the Fragment p-value. P-value is highly significant, showing 0.0029, which is highly significant. So next step should be the Fragment, postdoc Fragment in Nemeni postdoc test. So the function is postdoc.fragment-nemeni.test, and this function is available in PMCMR package that if you don't have, you have to install it. So we'll use the postdoc dot fragment dot nemini.test, and we pass the y within that, and that will give you the pairwise comparison using Nemini postdoc test. And this matrix, the lower triangular matrix, indicating the corresponding the p-value adjusted method, the adjusted p-values. And if you see, say A, B are not significantly different, whereas the significant difference, because A and C, A and E are significantly different, A and F are significantly different. Similarly, T, D and E are significantly different, D and F are significantly different, rest are not at all significantly different when you are do the pairwise comparison. Next, we'll see how to generate an empirical distribution function. The easiest way to estimate the empirical distribution CDF, use the rank and the length of functions. The ECDF function that is available computes the empirical cumulative distribution function. ECDF.KSCI plots the empirical distribution function with confidence interval. By manually, if you want to do, you can just say n equals to 100 and then x equals to normal r norm n. So suppose 1000 x values we have generated from standard normal distribution, and then the estimated degrees of distribution function is, as I mentioned, that rank and length might help you. So rank of x divided by length of x, and plot will, if you just plot x comma EDF, so plot EDF against x will give you the estimated distribution function. Alternatively, one can use the plot EDF x lab equals to x, y lab is this, and the grid. If you need the grid within the plot, you can just call grid after the plot function. It will generate a grid over there. And now the next option is to use a function ECDF.KSCI that I mentioned in the previous slide. So it is available in the library SFS MISC. So if you don't have, first you have to install the library and load it, and then only you can use this function. Just pass x within that function, then automatically it will generate the CDF as well as 95% confidence interval, the KS band, that Kolmograph's-Smirnov's band will be generated there. So there will be three plots. The middle one is the estimated distribution function, and left these two red lines indicating the 95% confidence interval. The Kolmogorov-Smirnov test. It is generally a very difficult to interpret the EDF directly. It is possible to compare an EDF to a hierarchy, theoretical cumulative distribution function, or to another EDF. Among the statistical tests that implement such a comparison is the Kolmogorov-Smirnov test, which is implemented by R function ks.test. One sample Kolmogorov-Smirnov test can be applied in this form, say ks.test x p norm. So x that we have generated from standard normal distribution, and the null hypothesis p norm that given. If it is not significant, that means it is a normal distribution. If you see, it is yes, it is 0.6081, so it is not at all significant. It is not significant means null hypothesis is true. That is, null hypothesis was it is normal, it is not equal to normal. So null hypothesis is true, it is normal. The two sample Kolmogorov-Smirnov test can be applied by passing two variables together, separated by comma. Say another variable you can generate from uniform distribution of the same length, and pass x comma y, ks.test x comma y. That will give you the d and the p value, and two-sided test by default. So p value is much lesser than 2.2 into the power minus 16. So it is almost 0. So it is statistically significant. Next, we'll learn how to generate the density plot. This is one of the non-parametric way of getting the distribution of the data instead of finding a parametric distribution, the matching of parametric distributions. Though that this density plot might also give you the idea about which parametric distribution can be approximated, but the density plot is actually non-parametric way of, or empirical way of getting a distribution of any data without assuming any rigid parametric function. The histogram is one of the methods to get a density estimations, get an idea about the distributions. To draw a histogram, there are different methods of drawing histograms. The default method is Sturges, that is suppose x is generated from normal, this is simulated data, x is one variable, and if you pass x and breaks equals to Sturges and probability equals to true, the distribution density estimation would be based on Sturges technique. And this is Sturges, which is 1926, the choice of class interval, Journal of American Statistical Association. Then the density estimate for the Friedman is 1981, et al. 1981, on the histogram as a density estimator, L2 theory. So this can be done by just mentioning breaks equals to FD. Sturges, instead of Sturges, you just breaks equals to FD in the same, then it will be generated. And the Scott 1978 on optimal and data-based histogram biometrica. Same way you can do, just write breaks equals to Scott. Then 1995 database choice histogram bandwidth, the American statistician. So here the library kernel smooth you have to call. Now H equals to DPH X and beans equals to say sequence minimum X minus H to maximum X of X plus H by H, and then histogram X breaks equals to beans and probability equals to true. That's the way you can draw the density for now according to the paper 1995. The kernel density estimation. The density is a function that might help to generate the kernel density, get the kernel density estimate. The choice of the bandwidth selection method with BW, check the sensitivity of the bandwidth choices using adjust. The default is 1. It is good practice to look at adjust 0.5 and adjust 2. So the plot density, the function is density, pass the value x within the density function x, then bandwidth is in 0, adjust 1, kernel is Gaussian, column is color equals to 1, then line another x, then inner 0, adjust 0.5, kernel Gaussian, then adjust up to 2. So there are 3 choices that are adjustment 1, 0.5 and 2. And the top right legend equals to, you can write the legend as a top right, where the legend is C, adjust equals to 1, adjust equals to 0.5, adjust equals to 2, and color 1 to 3, LTI equals to 1, and that will give you a kernel density plot. One can choose the kernel function with kernel Gaussian, kernel rectangular, triangular, by weight, cosine, optocosine, whatever you want. A lot of choices are there. For further details you can see the help of that particular function density. And this is the same thing that instead of all Gaussian, we just change from Gaussian to other different density function, parametric function as a kernel kernel. So Gaussian to rectangle to triangular kernel, and that has been plotted here. So it's and then the bivariate kernel density also can be plotted by the KD2D mass estimates a bivariate kernel density, and this is the mass package. So from mass package you will get these functions. You have to load the mass package. I mean, for example, say for bivariate normal distribution, say x generated from the standard normal and y generated by 1 plus x square plus r norm 1000, and then x and y, so dd is kd to d y comma x will give you the bivariate density function, and that can be plotted. One is contour, another by image. The left side is the contour plot, CONTOR contour. If you pass d, it will be a contour, and right side is the image. If you pass d, that will give you the image function, image of this bivariate kernel, and that will give you some idea about the bivariate kernel density and even univariate and bivariate kernel density. So I think that's cover more or less the non-parametric basic non-parametric statistics might be required at this stage. In this module we have learned how to apply the Fragment rank sum test in R, and then how to generate the empirical distribution function, and how to perform the goodness of non-parametric goodness of fit test through Kolmogorov Smirnov test, and how to generate the density plot in R.